Hello everyone. In this lesson, we're going to continue with the overall topic of parametric equations, and specifically, we'll talk about modeling motion with parametric equations. Now, modeling means to take a situation and represent it with various mathematical things, right? So for example, maybe you take a situation and you write an equation to represent it. Or maybe you represent it with a graph. So maybe the equation in this graph represents some object flying through the air. Maybe this equation and the graph give the height of an object over time. Or maybe you represent it with a table. And modeling is important and useful because it allows us to calculate and predict things about the situation we're modeling. In particular, this modeling is important for motion of objects because if you think about it, life is full of things that move, that display motion, right? And so maybe you work for an aerospace company and you're trying to model how things move through the air, airplanes, space shuttles. Maybe you're working on navigation and you need to track how ships move and travel through the oceans. Maybe you want to model planetary motion and you're trying to calculate how stars or planets move. So, let's see how we can model motion, specifically motion in 2D space, using parametric equations. So, before we use parametric equations, let's briefly review something that you may have learned in your previous work, and that is constant rate of change and linear functions. So constant rate of change means something is changing, increasing or decreasing at the same speed as time goes on. So constant rate, the same change per unit of time. So here's an example. It says, Mr. Oklahoma currently has $380 to use on recreation. He spends $50 each week on tea and pastries at a local cafe. And so remember, this type of situation can be modeled by a linear function or a linear equation. So let's say M for money, and then this person starts with $380. But now every week, the money decreases at the same rate, so minus 50 per unit of time, 50t. And then the graph at time 0 or week 0, the money starts at 380 and then goes down every week at the same rate, minus 50, minus 50. And again, the graph is linear, it's a line. So here's our first example with parametric equations. It says, suppose Becky is flying a model helicopter. The helicopter takes off from a bench 1.5 feet from the ground. It travels 3 feet per second in the horizontal direction and rises at a rate of 0.5 feet per second in the vertical direction. Model this situation with a table, an equation, and a graph. So first, let's discuss a couple things. Like in our previous lesson with parametric equations, note that we're graphing x and y, the helicopter's horizontal and vertical position on this graph. So the horizontal axis will be x, and the vertical axis will be y. And so notice, unlike our last example, t does not show up on the graph. T is our parameter, right? And again, you can think of it as time, which does not show up in our graph. So we'll be labeling our helicopter at each point in time. So we're thinking of this helicopter as literally moving in 2D space over time, with its x and y values changing over time like this, right, flying through the air. So now let's come up with equations to model or represent all this. And an important thing to know about 2D motion is that often you can think of the horizontal movement and the vertical movement independently, as in separately from each other. So we'll come up with an equation for the horizontal movement, as in the x position equals an equation. And then separately, the vertical movement, so a separate equation, y equals. Oh, also, before we move on, let's figure out where the helicopter starts. It says takes off from a bench 1.5 feet from the ground. So that's a height, right? That's vertical. And then it doesn't say anything about horizontal position, so we'll just start it at x equals 0. So x equals 0, but then 1.5 feet from the ground. So here, let's say. So the helicopter's initial position is 0, 1.5. And now, if you read the problem, notice that both the horizontal and vertical movement are linear. It's constant rate of change because it says the helicopter travels 3 feet per second in the horizontal direction and then rises at a rate of 0.5 feet per second in the vertical direction. So actually, let's start with vertical first. The helicopter, it starts at 1.5 feet above the ground, right? And then it says rises at a rate of 0.5 feet per second. So rises, its height is increasing, so plus 0.5 per second, so 0.5 per t, 0.5 times t. And there's our equation for the vertical movement. And then the horizontal movement, it travels 3 feet per second in the horizontal direction. So again, it doesn't tell us where it starts horizontally, so we'll just start it at 0 horizontally, plus 3 feet per second, so we're adding 3 to the x position per second, so 3 times 3t. Now, of course, if it's starting at 0, we're just adding 0, so we don't really need that, so we could just say x equals 3t. And now we've got our equations that model the motion. And we can use the equations to get the table and the graph. So remember how this table works. You plug in the time values, the t values, and that gives you the x and y position of the helicopter at those times. So for example, at t equals 0 seconds, you plug it into here for x, so 3 times 0 is 0. And then also plug the time in for the y to get 1.5 plus 0.5 times 0. So 0.5 times 0 is nothing, plus 1.5, so 1.5. Of course, that makes sense because we already knew where it was. But anyway, if you do this process for all the t values, then you should get the following table. So now we've got the x and y values at each time. And remember how to graph these points. For each time, we have an x and y position, as in a point on the graph. So at t equals 0, 0, 1.5. And again, I'm going to label the times. So this is the position at t equals 0. And then if you do that for all the points, you should get the following graph. So here's the graph. And this makes sense, right? With each second, this helicopter is rising a little bit in this direction. And during each second, this helicopter is traveling 3 feet horizontally and half a foot, 0.5 feet vertically, rising. And so there's the helicopter's motion. We've modeled it. We could use the equations, the table, the graph to predict or calculate where the helicopter will be over time, as in where the helicopter will be as time goes on, or where it will be at certain moments in time. So specifically, how would we go about calculating things? So first off, I got our equations in our model here. And then some questions. What would the helicopter's position be after 8 seconds? Now this one's pretty straightforward. That just means t equals 8, right? So you would just plug in 8 for t in x and y. For x, you'd get 3 times 8 is 24. For y, you'd get 1.5 plus 0.5 t is 8. 0.5 times 8 is 4 plus 1 plus, so 6.5. So you would say the helicopter's position is 24 for x right here, and then 6.5 for y. And here's the final answer as a coordinate point. Now, next one. When the helicopter is 10 feet above the ground, what is its horizontal position? So a helicopter 10 feet above the ground you have to read that and think, okay, that's a y position, that's a y value. And then what is its horizontal position? That's asking us what is the x when y is 10. So notice with our equations, they've given us y. They're asking us to find x. And we don't know the time involved, right? We don't know the time that this helicopter is 10 feet above the ground. So the process here goes like this. You're going to use the y value that they give you to find what time we are at when the helicopter is at 10 feet vertically. And we're going to use that time for when y is 10 feet. Use that same time to find what x is. So y equals 1.5 plus 0.5t. So that means 10 equals 1.5 plus 0.5t with our time unknown. And then this is a simple linear equation that you can solve for t. Subtract 1.5. These go away, you get 8.5 equals 0.5t. Divide by 0.5t, or 0.5. These go away, and you get t equals 17. And remember, this is 17 seconds. So at 17 seconds, the y value is 10. And so at that time, when t is 17 and y is 10, what is x? So now we can plug this t value into our equation for x. X equals 3t, but t is 17. And so we get x is 51. And you know, this is representing some real world situation, so don't forget the units. X is 51. What is the units? That's 51 feet, right? And so again, we've calculated a horizontal position for the helicopter, an x value given a y value. So next example, suppose a self-driving car careens off of a cliff 50 meters above the sea. It is driving at 5 meters per second. Suppose the car is at the very edge of the cliff at t equals 0 and the point at the edge of the cliff is 1050. Model this situation. Approximately how many seconds does it take for the car to hit the water? So first off, let's draw the initial situation. So it says the car is at 1050, so 10 meters horizontally, 50 meters vertically, so around here. And then let's draw the cliff. And then 50 meters above the sea means the sea is at 0 in our graph. Here's the car at 10, 50. That's its XY position at t equals 0 seconds. And it's driving this way off the cliff at 5 meters per second, right? Now again, note that when something is falling through the air, even then we can consider its horizontal and vertical movements separately. So x equals and y equals, we're going to come up with equations for the vertical and horizontal movements separately. And while it's on the cliff, it's going at 5 meters per second, right? And actually, when it falls off, its horizontal movement, again, independent of the vertical movement, it's just going to keep going at 5 meters per second. So 5. Although don't forget that it starts at 10 meters horizontally, so 5t plus 10. And so when something is falling through the air, it actually falls like a parabola, but the horizontal movement is still going to be linear. It's still going to be constant rate of change like this. And then anything falling through the air, its trajectory is going to be a parabola. So you may have learned in physics or some other science course that the height of an object falling through the air, subject to gravity, can be modeled with an equation like this. Y equals, and then the starting value minus half the acceleration of gravity, which in meters and seconds is 4.9 times time squared. It's actually more complicated, but for this example, we'll just keep it like that. So what's the starting value for the y position? The car is at 50 meters above the water, right? And then minus the acceleration of gravity, 4.9 t squared. And so there's our equations for our model. And if you plot some points in a table, you get the following. And then if you plot those points on the graph, you get a curve like this. And again, it's a parabola. By the way, know that when something falls through the air, over time, that thing starts falling faster and faster and faster, which is why it's not a line, it's a parabola that gets steeper and steeper as we go. Now, it says approximately how many seconds does it take for the car to hit the water? So here's where it hits the water, right? And notice that we have 2 points, one at t equals 3 seconds, one at 4 seconds, where at 3 seconds it was positive 5.9 was the y value, so it was above the water. But then at 4 seconds, we got this point, and the y value is negative 28, so it's below the water. So that tells you, okay, this car hit the water sometime between 3 and 4 seconds, right? So 3 point something seconds. So note the significance of the positive and negative y values in the context of this water, right? And note that this makes sense on our graph because here's the point when t equals 3 seconds. Down here is the point when t equals 4 seconds. So then the time at which the car hits the water is somewhere in between those two, right? Between 3 and 4 seconds, 3 point something. Now, between 3 and 4 seconds, that is not a very precise answer, so we could also calculate it exactly. Now, how do we do that? Approximately how many seconds does it take for the car to hit the water? Hit the water means its y value is at 0 here, right? So what you do is you're like, well, we want to know the time when y is 0. We have our equation for y, so plug in 0 for y equals 50 minus 4.9 t squared, and this is just an equation that we can solve for t. So subtract 50 from both sides. These go away. We get minus 50 equals negative 4.9 t squared. Divide by negative 4.9. These go away. So t squared is around 10.204. And then how do you get t by itself? Square root. And you get that t is around 3.194. And again, this is a real world context. So what's the units? Well, it's seconds, of course. And you know, this answer matches what we were saying about between 3 and 4 seconds, right? So there you have it. That's the answer we were looking for. The car hits the water around t equals 3.194 seconds. And sorry, I had to do some weird editing, so the work is gone now. Of course, you can rewind and go back in the video to look at the work. And that's it for this lesson. Good luck.